Hi everyone, this video is going to talk through the electromagnetic spectrum. We have some few key ideas over here to talk through. We've got wavelength, frequency, how does energy relate to all of this. We'll talk about what exactly is an electromagnetic wave, look at the spectrum, and then talk about visible light. So our notes are a little bit different. You're going to be just kind of looking at different pictures, and we're going to talk through those figures to make sense of them. So up first, we're going to talk about wavelength. So wavelength is often abbreviated with a symbol that looks like this, and it is the Greek letter lambda, so that's a Greek L, and that is the symbol for wavelength. And the definition for wavelength is really just the distance from one point on a wave to the distance of that same point on another wave. Some people like to use the crest of the wave, like here and here, in order to make the wavelength, but really the wavelength could just be the same point. So we could go from here to here, and that's a wavelength, or we could go from here to here. It doesn't really matter, it just has to be a full wave cycle. So the wavelength, the definition that we're going to write down, is the distance from one point on a wave to the same point on another wave. And as you can see, the wavelength changes. So we have something that has a really short wavelength here, versus here we have a much longer wavelength. The waves are more spread out. And so naturally, then talking about wavelength, we start to look at something called frequency. So we've talked about wavelength. Up next, frequency is how often, how frequent a wave repeats. So right here we see high frequency. So this wave is repeating very, very often. It's very short. It repeats itself often. So it has a high frequency. Something that has a low frequency would have a much longer wavelength because the wavelength takes longer to repeat. So frequency is abbreviated with a fancy curly Q F, and it looks kind of like that. So to define frequency, we're just going to define this as how often our wave repeats. So how often the wave repeats. Now we could be really specific and say a certain amount of time. So the frequency could be per second or something like that. But we're just going to be kind of general, just how often the wave repeats. So if we look at something with a high frequency, it's repeating a lot. So it has a high frequency. Something with a low frequency, it doesn't repeat very often, so it has a low frequency. So let's talk about the relationship between wavelength and frequency. We can see here that a shorter wavelength is a higher frequency versus a longer wavelength is a lower frequency. So they're starting to look like opposites. As our wavelength decreases, our frequency increases. And then as our wavelength increases, the frequency decreases. So let's jot that relationship down. I'm going to use the symbols, and I'm going to say a larger wavelength means a lower frequency. And then the converse is true too. A shorter wavelength means that we have a higher frequency. So to summarize those two things, we notice that these are opposites, right? As the wavelength gets larger, the frequency gets smaller, and vice versa. The shorter wavelength, you get a higher frequency. So we're going to say that these are indirectly related because they're opposites. So wavelength and frequency are indirectly related, which just means that they are opposites. So we've already talked about wavelength, now we've talked about frequency, but let's talk about energy as well for how this relates. So a wave carries energy with it. And if a single wave carries a certain amount of energy, then the more often we have a wave repeating, the more energy is being seen. Versus with a long wavelength, low frequency, the waves are occurring less often, so therefore we have lower energy. So a wave carries energy. Therefore, the more we see that wave repeating, the higher energy it will have. So we said that waves carry energy. And therefore, that's what those three little dots mean, therefore, a higher frequency means higher energy. So because these go together, they are directly related. So they go together. So we've put frequency and energy together and showing that they're directly related, but let's compare frequency to wavelength as well. So let's make one chart that summarizes all of this in terms of wavelength, frequency, and energy. So we've got wavelength, frequency, and I'm going to use a capital E for energy. So let's talk about how these are related. So let's say we have a larger wavelength. Then we know that larger wavelength, our frequency is going to be lower. And that means the energy is going to be less because one wave carries a certain amount of energy with it. Wave is occurring less often because it's larger, less energy. And then the opposite is true. If our wavelength is getting shorter, that means our frequency is going to be higher, which means now we have more energy being carried with that. So we said wavelength and frequency, those are indirectly related. And then that means that wavelength and energy, the wavelength and energy are also indirectly related, whereas these two were directly related. All right, and that finishes how does energy relate. The next thing we need to talk about is what exactly an electromagnetic wave is. So before we talk about the electromagnetic spectrum, let's talk about what exactly an electromagnetic wave is. So an electromagnetic wave is different from a traditional wave, like you can think of an ocean wave or a mechanical wave, because it doesn't require a medium. It doesn't require matter in order to carry it. Something like a sound wave, the only reason we can hear a sound wave is because it travels through the air. We have a medium to help us experience it. Electromagnetic waves don't require a medium. They can travel through empty space, like the vacuum of space. And there's two different parts to an electromagnetic wave. We see this electric field here, but then we also have a magnetic field. And electromagnetic waves happen because of the interaction between electric fields and magnetic fields. These two fields influence each other, and a change in one of these fields will create a change in the other. For example, you could take something like a regular nail, you could wrap a wire around it, and then if you attach it to a battery, now as you pass an electric current through that nail, it becomes magnetic. So these two fields interact with each other. So a change in the electric field will result in a change in the magnetic and vice versa. So let's jot that down. So changes in the magnetic field will change the electric field and vice versa. So these two fields are tied very closely together. And the reason that we know that they are tied so closely together is a scientist named Maxwell. And in the 1860s to the 1870s, he noticed this phenomenon that electromagnetic waves were this single unit, and he noticed that changes in the electric field and the magnetic field went together, and so he developed a full system of equations about that. We're not going to go into depth with that. That's more of a physics side of things there. We do need to jot down before we move on that these waves do not require a medium. And this is just like we mentioned before, that these waves do not require matter, which is medium, in order to propagate moving forward. They can travel through empty space. Okay, let's check off electromagnetic waves. Next, we're going to talk about is the electromagnetic spectrum. So you've already spent quite a bit of time on this, and you've researched all sorts of different parts of the electromagnetic spectrum, from how a microwave actually works to what can we use gamma rays for and that sort of thing. So let's notice we've got a measurement of wavelength here, and we've talked a lot about wavelength already, and this is in meters. And then frequency is measured in hertz. And so we can see that these are opposite, right? So we can see the relationship here. Wavelength here is a lot larger, frequency is lower. Here the wavelength is smaller and the frequency is higher. I would encourage you to grab some sort of coloring utensil and fill this in with some colors. That way you can refer back to. But let's write down some things that we see. So on this side of the electromagnetic spectrum, our wavelength is larger. So we have that larger wavelength, which means we have a lower frequency and therefore less energy. On the other side of our electromagnetic spectrum, we have a much smaller wavelength, which means we have a higher frequency and therefore more energy. So you're going to need to know how to put these in order. For example, from let's say largest wavelength to smallest, you've got radio, microwave, infrared, visible, ultraviolet, X-ray, gamma, and that sort of thing. So make sure you can put these in order. We also want to zoom in for just a moment on this visible light section. So visible light here is broken down into the different colors we see. So for this, let's talk about the energies with it. So on this side, we've got red, so Roy G. Biv. Red has the largest wavelength, then the lowest frequency, and the least amount of energy. And these all have measurements that go with them, the colors do. We can measure their wavelength or frequency as well. And then on this end, we have the smaller wavelengths, the higher frequency, but there's more energy. So if we were to order the colors of visible light from less energy to more energy, we would follow along this direction. We would say red, orange, yellow, green, blue, indigo, and violet, and that would go in order that way. So make sure that you can look at the electromagnetic spectrum and you can analyze it really in terms of wavelength, frequency, and then the energy that goes with that. The last piece we briefly mentioned already, which is visible light. So visible light, as we see it, like from a light bulb, we see white light. However, white light is actually made up of all of the colors. So what we can do is we can take white light and pass it through a prism. This is a prism. And then it breaks apart into the different colors. So we can see red all the way down to violet, and then we've got some measurements here as well that we can take a look at. So the reason that this is broken apart is because the light gets refracted into its different colors, and then the amount that it deviates, just a little bit versus a lot, will show us what color it is. So things to remember, white light is made up of all the colors. This prism is refracting light, so it's undergoing refraction. And then here's the part that we're going to really connect to in a couple levels, which is that we can use the colors given off by elements in order to determine that element. So we can look at the light an element gives off and do some interesting things to figure out what exactly that element is. All right, so that covers a little bit about visible light that you guys need to know. We've talked about wavelength and frequency and energy and how those are related and whether they're indirectly or directly related. We've talked about electromagnetic waves and how they are really just integrated together. We've talked about the electromagnetic spectrum and what that looks like in terms of wavelength, frequency, and energy. And we talked about visible light and what exactly that is made of. That is it for electromagnetic spectrum notes.